Sagarika, in module 9, we will still deal with the block design in a very general framework. Maybe now we will specialize to RBD, randomized block design, and see what are the simplifications and why the analysis of an RBD is so simple. There must be an underlying reason for that. We will try to understand in the process the concept of what is called orthogonality in a block design. So let's see what is coming up. We will take some interesting exercises and MCQs at the end as well. So let's see what is coming up now. Sagarika, you may recall that in the context of a general block design involving B blocks and V treatments, we introduced the notion of incidence matrix capital N, and its elements were Nij. Nij refers to the number of observations corresponding to the combination treatment I and block J.
Yes.
Now, such a block design could be designated as a binary block design if Nij is just 0 or 1. That means in a block, either a treatment shows up or not, the incidence pattern is 0 or 1, that is called a binary block design. And in a randomized block design, it is a very special type of binary block design, where every block is complete in the sense that every block receives every treatment exactly once. That is why it is called a randomized block design, in short RBD. So in a way, RBD is defined by the unique feature capital N. The incidence matrix is a matrix of all ones, which is in matrix notation the matrix J. J is the matrix of all ones. Every treatment occurs in every block exactly once. That is how an RBD is characterized.
Sir, it is interesting to note that for an RBD, the C matrix specifies to C is equal to B into 1 minus capital J by V. So that C plus, that is the G inverse of C, is equal to 1 by V into I minus capital J by V. And hence tau hat has this expression upon simplification. So this suggests tau I minus tau I prime is estimated by y bar I naught minus y bar I prime naught, and this is independent of block parameter estimates. Sir, I am sure likewise beta j minus beta j prime is also estimated by y bar naught j minus y bar naught j prime independent of treatment parameters estimates.
Yes, you may also note that for an RBD, the covariance between the difference between two treatment means and the difference between two block means is equal to 0 for all such comparisons. When this obtains, we say that the two classifications are orthogonal.
Okay.
Therefore, RBD is the simplest example of a two-way orthogonal block design. In case the incidence matrix is different from the vector of all ones, it could still mean orthogonal classification, but not necessarily. It follows that capital N of the form R prime k divided by n provides an orthogonal classification where n equal to sum of all the observations in the number of observations in the design.
Okay.
So the form capital N equal to R k prime over small n, that signifies that Nij equal to Ri kj by n. That is how it's called proportional cell frequency.
Okay.
In case capital N admits of any zero element, the classification or the block design is necessarily non-orthogonal, because capital N of the form Ri kj by n, that can never admit of any zero value. Whenever you have got some zero element in the matrix capital N, you can immediately conclude that the design is non-orthogonal.
Okay.
In fact, in the above, we have discussed about analysis of a non-orthogonal connected block design. These are further elaborated below. A block design is said to be minimally connected. Minimally connected, that means there is no degree of freedom left for the error.
Yes.
You have got just enough bare minimum number of observations to make sure that the design is connected in the sense of treatment connected as well as block connected. Okay, so you have scarcity of experimental material, with just enough number of observations to make sure that you can ensure just the connectedness and nothing beyond. That means the error degree of freedom equal to 0. We know the expression for the error degree of freedom, the count number, n minus b minus v plus 1, that has to be equal to 0. Therefore, n equal to b plus v minus 1. That is the minimum number of observations that you need to ensure connectedness, and you have no degree of freedom left for the error. This happens when you have resource crunch. A block design is said to be orthogonal if and only if the estimates of the treatment differences are uncorrelated with the estimates of the block differences. You stipulate that the design is connected, and then you want that the covariance between the treatment difference estimate and the block difference estimate should be equal to 0 because of uncorrelated nature. And then you can show that a block design is orthogonal if and only if, as I said earlier, capital N equal to R k transpose by N. That means Nij equal to Ri into Kj by N. And that shows that the rank of the capital N matrix is 1. This condition too gives rise to a design which is called a proportional cell frequency. Ri into Kj by N, it gives you proportional cell frequency. RBD is the simplest example of its kind. When all the Ri's are equal, all the K's are equal, therefore you have got capital N equal to a matrix of all ones. And when this obtains, as you saw earlier, the expression for the treatment sum of squares, that reduces to simple expression like this, and the expression for the block sum of squares becomes like this, as if there is no difference between adjusted and unadjusted. Okay, whatever is adjusted remains as unadjusted, whatever is unadjusted remains as adjusted, because of orthogonality of the two kinds of estimates. This explains why analysis of an RBD is extremely simple. Let me now go ahead and introduce the concept of a random effects model in the context of a block design. Earlier we saw that in the context of a CRD, random effects model was introduced. There we assumed that we have a large number of treatments to be compared, and because of resource crunch, we cannot accommodate all of them in the experiment. We accommodate small v out of capital V. That is how the concept of random effects model crept in the context of CRD. Now we consider a block design setup with B blocks selected at random from a large collection of capital B blocks, and also small v treatments selected at random from a large collection of capital V treatments. So originally we contemplated on having an experiment with capital B blocks and capital V treatments, but that would naturally call for a large number of experimental units, and because we have resource crunch, so we think of small B blocks and small V treatments somehow to accommodate a connected block design. Thus, in effect, we are now in the setup of a block design with what we call random block effects and random treatment effects, because the B blocks and the V treatments are selected at random out of larger collections. We refer to the earlier model, and this time we modify the model as mu plus Ti plus Bj plus epsilon ijh. So we are referring to a very general block design where yijh refers to the output corresponding to the hth replication of the ith treatment in the jth block, and that h goes from 1 to nij, and we assume nij to be positive. Now the expression to be noted is that now we are no longer writing tau, we are writing Ti. We are not using beta j, but we are using Bj. In fact, these notations make it clear that we are referring to a random effects model rather than a fixed effects model. So you will see in standard textbooks that they always make a difference among the in using the notations. That's very important. The moment I write mu plus Ti plus Bj, you know that I am referring to a random effects model. If it is mu plus tau I plus beta j, it is a fixed effects model. So here Ti and Bj, they correspond to the random effects for the treatments as well as for the blocks. And of course epsilon I is, those are the standard error components. So we set expected Ti equal to expected Bj equal to 0, variance of Ti, that is one component of variation, sigma square T, variance of Bj, other component of variation, sigma square B, and of course we have variance of the error, good old sigma square E, and we assume that all covariances are 0. So in a way, this model is now referred to as a random effects model, and the central problem is that of estimation of the three variance components, pure error sigma square E, the variance component due to treatment effects variation sigma square T, and that due to the block effects variation sigma square B. It is mainly now called a problem in the context of ANOVA variance components estimation.
Okay.
We are supposed to estimate the three components of variance given the data. When the block effects are fixed but the treatment effects are random, or the reverse happens, we say that we are in a mixed effects model scenario.
Yes, sir.
To look at the expression number 5, we are writing Ti plus beta j, and in expression 6, we are writing tau I plus bj. The notations are self-explanatory.
Yes, sir.
Whereas 5 refers to a model where Ti is used instead of tau I, so it is a random effects model with treatment effects random. 6 refers to a random effects model with block effects random. And accordingly, 7 corresponds to the expression 5, where you have only two variance components, sigma square T and sigma square E, and 8 refers to expression 6, where you have other two variance components, sigma square B and sigma square E. So we need to test equality of the fixed effects and estimate the variance of the random effects. So with reference to model 5, whereas for the blocks we have the fixed effects, we need to test whether the block effects are equal or not. For the treatment effects, we need to estimate the variance component sigma square T. Similarly, for model 6, we need to estimate the variance component sigma square B, and we need to test equality of the fixed treatment effects tau i's. So that is how the model is interpreted and the inference problems are posed.
Okay.
So in module 9, basically we talked about the concept of orthogonality of a block design and naturally the concept of non-orthogonality. What is meant by orthogonality, how is it achieved, what is the expression for the matrix capital N, the incidence matrix, and then what is the minimum number of observations that are needed for a design to be connected and orthogonal. And if it is non-orthogonal, then of course that is very easy to see that the blocks and the treatments, they are separated in different groups. So we had questions involving connected orthogonal designs, connected non-orthogonal designs, etc. I hope that one gets a good feel of the block designs in general involving these two basic concepts. In real life application, we always try to get a connected block design, whether it is orthogonal or not, because if the block size is incomplete, then invariably some Nij may be 0, and the moment Nij equal to 0, the condition of orthogonality is hopelessly not satisfied. Therefore, the design turns out to be a non-orthogonal design in case some Nij equal to 0. Because the condition Nij equal to Ri kj by n, in order that that condition is satisfied, Nij has got to be strictly positive and integer, of course. So whenever we have an incomplete block design, that is the simplest example of a non-orthogonal block design. Okay, I think with this we will stop. Let's see what is in store for us in module number 10.
So, sir, the first question is, give an example of a non-binary connected orthogonal block design with treatment replications given by 6, 3, 3, 3, 6.
Okay, let's see. The moment it says non-binary, you know that Nij has to be more than 1 for
Yes,
at least one treatment. Therefore, RBD is ruled out straight away.
Yes.
Because RBD refers to not only binary, RBD refers to
One,
capital N equal to matrix of all ones.
Yes.
Every treatment has to appear in every block exactly once and once only.
Yes.
That is the formation of RBD. The moment you say non-binary, it is ruled out. The moment you say orthogonal, Nij cannot be 0 either. No 0 is there.
Yes.
So the treatments have to appear in the blocks. Every treatment has to appear at least once in the block,
Yes.
and we have to make sure that the design is orthogonal. Orthogonal means proportional cell frequency. Therefore, Nij has to satisfy the formula Nij equal to Ri kj divided by the total number.
Yes.
So with that understanding, we have to construct the example.
Yes, sir.
So the treatment replication numbers are given by 6, 3, 3, 3, 6. We have to find out. So we can see that there are 5 treatments that we are talking about. Treatment replications given. So there are 5 treatments.
Yes.
V equal to 5. And they are total numbers are 6, 3, 3, 3, 6, we have to figure out how many blocks we are talking about and then what are the incidence numbers so that they satisfy the condition of orthogonality.
Yes.
It's not difficult, but you have to figure out
Yes.
how many blocks you are dealing with, okay?
Yes,
What is
I
the
understand.
next question?
So the next one is we need to give an example of a non-binary connected orthogonal block design with treatment replications given by 18, 12, 12, 12 and again 18, and with the block sizes 24, 12, 12 and 24.
Very good. So if we look at the capital N matrix, now the number of treatments is 5 and number of blocks is 4. So capital N matrix is of order 5 cross 4. You write out a blank matrix of order 5 by 4. You know that the row totals, they refer to the treatment replications. Those are 18, 12, 12, 12, 18.
Yes.
And the column totals, they refer to the block sizes.
Yes.
Those are 24, 12, 12, 24.
Yes, sir.
You figure out these two totals in the margins. Now you try to figure out the numbers Nij which will satisfy orthogonality, means any number Nij equal to corresponding row total into column total divided by the grand total. You know the concept of orthogonality.
Yes, sir.
Ri into Kj by n. So whatever the number you want to put, you have to make sure that it is equal to corresponding row total multiplied by column total divided by grand total. This is a relatively simple problem because you know the row total, you know the column total and you know the grand total. You just do the computation and put it there.
Yes, yes,
Well, that is how we can come up with a matrix capital N.
yes.
So question number 2 is pretty obvious.
Simple, yes,
Okay.
yes, sir. The third one is we need to give an example of again a non-binary connected non-orthogonal block design with treatment replications given by 10, 8, 8, 8 and 12, and with block sizes 10, 10, 12 and 14.
Okay, this is a bit
So,
tricky.
yes.
It says that you have to give a non-orthogonal block design.
Yes, yes.
So imagine you write out a capital N matrix and then you know what are the row totals and the column totals and then pretend that you are trying to construct an orthogonal design, row total, column total by grand total, and then you will find that something is missing somewhere. You cannot quite get integer solution.
Yes.
So put some numbers so that they add up to these totals.
Yes, yes, sir.
Okay, this question is not difficult because they are asking about non-orthogonal. It could be any number which do not satisfy the orthogonality condition
Yes.
and they match with the row and column totals. Okay,
yes,
it's
yes.
also a relatively simple question.
Yes, sir.
Okay, let's look at the MCQ.
Okay. So the first one is a non-binary connected orthogonal block design involving V is equal to 7 treatments and B is equal to 7 blocks must necessarily have block sizes. There are 4 options here. The first one is the block sizes should be at least 8. The second one is at least 9. Then at least 10. And the final one is none of the above.
Oh, very good. So they are referring to a non-binary connected orthogonal block design. So you know Nij is corresponding row total, column total by grand total. There are 7 treatments and 7 blocks. You imagine you have a capital N matrix 7 by 7 and you want to come up with a non-binary orthogonal block design and then you need to know what are the block sizes.
Yes.
Block sizes at least 8, at least 9, at least 10, none of the above. It's very interesting that what should be the minimum block size, it has to be different from an RBD.
Yes, sir.
You rule out RBD straight away because it says it is a non-binary design.
Yes,
Okay,
yes.
so because it is non-binary, you take it out, take out RBD. Now you need to know what is the minimum block size that you are contemplating so that you can have an orthogonal design. Very interesting
Yes,
question. Eh?
yes, sir.
Let's say, suppose I decide on in the first block, I decide on the treatment replications as there are 7 treatments. I decide on the treatment replications as 1, 1, 1, 1, 1, 1, 2.
Okay. Okay.
1, 1, 1, 1, 1, 1, 2. So there's for 6 of them it is all 1. The last one is 2.
Yes.
Therefore the total number is 8. Okay. I cannot have all of them 1, that would refer to RBD.
Okay.
Okay. So it has to be at least 8.
Yes.
If it is 8, I can figure out 1, 1, 1, 1, 1, 1, 2 and I can repeat the whole thing all over for all the blocks.
Yes.
So that is how one has to figure out.
Yes. Yes, sir.
What is the next one?
So the next one is a non-binary connected non-orthogonal block design involving V is equal to 7 treatments and B is equal to 7 blocks must necessarily have, and the 4 options are
Okay.
at least 55 observations, at least 65 observations, or it can be at least 75 observations and 70 observations, and the final one is none of the above.
Okay, it says non-binary. So you rule out RBD. Connected, it says non-orthogonal.
Okay.
So non-orthogonal means you cannot have that condition Ri(k)j by n. That's the only thing that you are told. That referring to 7 by 7. So you think of a matrix 7 by 7 and it has to be non-orthogonal, and then you are talking about what is the minimum number of total number of observations that you need. Okay, because it is non-orthogonal, the moment you put some 0, you cannot put 0 because it says non-binary. It has to be minimum of 1, etc. So you need at least 49 observations. Then it talks about 55. So they are giving various options. So non-orthogonal is very easy to catch. Orthogonality you need a condition. Non-orthogonal it's very, you can see immediately what is the answer. Okay.
So here is the third one. A non-binary disconnected block design involving V is equal to 7 treatments and B is equal to 7 blocks must necessarily have block sizes at least 4, at least 5, at least 7, or none of the above.
Interesting problem, because the moment it says disconnected block design, in the text we mentioned that you try to understand the concept of disconnected block design. Disconnected block design means the entire block design is separated. So there are some blocks involving some treatments, another set of blocks involving another set of treatments, and so on. There is nothing common between the two. That is the concept of disconnected.
Yes.
You think in terms of two groups. So the V7 treatments have to be classified into, like say 3 treatments in one group, 4 in another group. Like that 7 blocks.
So the third question is, a non-binary disconnected block design involving V is equal to 7 treatments and B is equal to 7 blocks must necessarily have block sizes at least 4, at least 5, at least 7, or none of the above.
Okay, so here the keyword is disconnected.
Yes, yes.
The moment you say that the block design is disconnected, you know that the blocks have been disconnected, so are the treatments. So generally, you can think of 7 blocks divided into 2 separate groups, 7 treatments also divided into 2 separate groups. Within one group, blocks and treatments they are together. In another group, another set of blocks and treatments are together.
Yes.
That is how the notion of disconnected design comes. If that has happened, then what is the block size, minimum block size that is needed? That's the question is all about.
Yes, sir.
It's not difficult, but you can immediately think of a disconnected. Then a non-binary means each one has got to be at least 1. Okay.
So we will try, sir.
Yeah. Okay, I think that is the end of it.
Yes.
I will try to summarize now the whole thing.
Okay, sir.